So with the elevator problems, we're going to start talking about a little bit of something that we can consider a little bit of a fake force. We'll get into this a lot more with circular motion, but this is going to be our first kind of idea of what a fake force might be. Okay? So these are referred to elevator problems because I'm guessing probably everybody's ridden an elevator, right?
Yes.
Do you have a question or are you just...
Sure.
Okay. So I want you guys to think about when the elevator starts going up, right? So when the elevator starts going upward, what does it feel like?
Your weight's going down.
Okay. You kind of feel like you're pushed into the ground. You feel almost heavier, right? Yeah?
Elevators as a especially the glass ones. Especially the glass ones.
Alrighty, guys. When you get to the top and the elevator is stopping and you shortly get to get off the elevator, which I'm guessing is Charlotte's favorite.
Yeah, I hate the crack and then I always hit the first. So I want to get shut in.
I see. So you're up at the top, the elevator's slowing down. What do you feel like up there?
You almost
feel like you're lifted up a little bit, right? You feel a little bit lighter, okay? Now, I want you to remember that because that's going to be really important when we get to what equation to use, okay? Now, if you are actually standing on a scale in the elevator, so if you decided to bring your bathroom scale with you and set it down in the elevator and stand on it.
Sometimes.
Yes, that's a scale. Your scale would actually read a different number when you're going up. It would actually read that you are heavier when you're going up. And when you get to the top, it would actually read that you are lighter when you're up at the top. Okay? So this is where we get this idea of apparent weight. Okay? This is the value that a scale is going to measure, but it's going to change based on how fast you're going or how much you're accelerating, not how fast you're going. Bad choice of words there. Okay? Yes.
Okay. So has this been proven before? Like if you take a scale on an elevator, then you're like different weights and stuff.
I want to do that.
Who took a scale on an elevator? Just like, hey, let's go measure our weight.
Well, I'm guessing they didn't. Okay, so you can do this different ways. It's just a lot more, I guess, thought-provoking in an elevator. So if I took this scale over
Yeah, we
here
listen to that.
and I put, I don't know, a pencil on it. I think the pencil will stay, or pen. Right? If I pull up, it's going to read differently than when I let it go down, right? So you can test this with a normal scale. Yeah. You see it jumping back and forth? Yeah.
That was a
Okay? So that is actually reading different weights.
So I'm gonna make a clutch stops at 12.
All right. So we're going to talk about how we can actually calculate it and how you're going to do your worksheet. Because this is actually pretty easy calculation-wise, but it can get a little confusing because it's a lot more of thinking about how to use the equation rather than just your plug and chug that you normally do in math. Okay? All right. So we have a person on the elevator. What is the mass of the person? Yes.
Oh, 75.
100.
75.
So you 75 is a normal amount of weight. Go 75.
You got to give me the units to go with it.
75
Okay.
75 pounds. No, that's 100 something pounds.
Okay, so 75 kilograms is actually a fairly reasonable weight. Or mass, sorry, mass.
It's not like 200 kilograms. It's not like 400 pounds.
Yes.
That's what we're looking at right
It's 405. No, you say it's 400.
No.
Okay, this is not relevant to our equation.
Yeah. So you just multiply this by 2.
159.
Yeah, so it's a completely reasonable weight. All right. So we've got 75 kilograms as our mass. If this person is on a stationary elevator, right? How would we calculate the weight?
9.81 meters.
That's not the weight, but it does involve that.
Multiplying.
Okay, we're going to use technically Newton's second law, weight equals mass times the acceleration of gravity, or 75 kilograms times 9.81 meters per second squared. So what's 75 times 9.81?
I don't.
You should get your calculator, it probably knows.
735.75.
So 735.5?
75.
75. Okay. All right, so notice, don't forget, weight is measured in newtons. It is a force. Your mass is measured in kilograms. This is going to be really important for your worksheet because there are some where I give you your weight, some where I give you your mass. When we get to the equation for this, it's also going to be really important. Okay? Good?
Wait, so
Wait,
you said weight still is the W, right?
Weight is W. It's measured in newtons. Then your mass is measured in kilograms.
Wait, is a stone a weight or a man?
Stone is weight, I'm pretty sure. Yeah, it's measure of force.
Yeah, it's
Well,
weight. That's what. Isn't that what like?
I think it's weight. It might be mass. I'm not actually 100% sure.
Isn't it like each one's like 20 pounds or something?
14.
Okay.
Somewhere around 14.
Who uses stone?
The British people.
All right.
I don't think
So-
I actually use them. I don't
Well, I was watching a YouTube video with the
Guys.
person in it and he used stone.
Let's look at our forces acting on this person. This person has its weight, right? This person also has the normal force from the elevator, right? Everybody good with that? Yeah? All right. So we can look at our equation here. F net equals ma, just Newton's second law. And we already know what our net force is, right? Well, in variables at least. Our net force is going to be our weight plus our normal force, because we're just adding up our forces, and that's going to give us ma. Okay? All right. I also just realized I forgot to define apparent weight, okay? Because that's actually going to be important for what we're going to do next. So your apparent weight is the supporting force on an object, okay? That's the force that makes you feel like you have weight. So your apparent weight is the supporting force. What else is the supporting force?
Normal force.
The normal force. The apparent weight is also the weight measured by a scale.
Wait, what?
So if you're standing on a scale, this is the weight that's going to be measured. So if you're standing still, it will be your actual weight. But if you're accelerating, it's going to be different than your actual weight. Okay? Yes.
Whenever you do science stuff, and like you're trying to get like a weight or something exact, like a person, like to do the research or whatever.
Yeah.
Like they wouldn't have to like get on the weight or get on the scale naked, would they? 'Cause, like, on
It
the-
depends on how precise it needs to be. You would probably have them remove their shoes and anything that's particularly heavy.
What you would do is you give them clothes and you know how much they weigh.
Yeah, or you could weigh your clothes separately. Yeah. Yes.
Is the worksheet gonna be, are we gonna grade in class?
All right. So here we want to find our apparent weight or an equation for our apparent weight. But we know that our apparent weight is our normal force. Okay, so we can solve this equation for our normal force. What we end up with is N, our normal force, equals MA minus our weight. Or we can make this look a little bit more like the equation on your worksheet
MG.
and change this to mg.
Why does it become G?
G just means that it's the acceleration of gravity.
That's it.
So it's specifying that it's not just any acceleration, it's whatever the acceleration is on the surface of that planet. In this case, it would be 9.81.
Wait, and this is defined
Apparent weight. Okay?
labeling.
Now, the signs with this equation get really, really tricky. So we're going to kind of ignore the signs and circumnavigate them and use our idea of if we feel heavier or lighter on an elevator, to figure out what our signs are going to be. Okay? Now, we're going to call, in most circumstances, right, we're going to call up positive. That means that there's going to be a negative sign here. It's going to cancel out with this. So we end up getting a positive mg in most cases. Okay? So we're going to change the way we're writing this, and we're going to just go with essentially the equation that is a little bit more intuitive. Okay? So if you are on an elevator and the elevator starts going upward, okay, so we're going up. Okay? We're going to start with our mg. We're going to start with our weight. Are you going to feel heavier or lighter?
Heavier.
You're going to feel heavier. So we want to add this extra term on to make our number bigger. So we're going to put plus ma. And like I said, we're ignoring signs here. So even if your acceleration was considered negative or something like that, just ignore it. In this case, we've already taken care of the signs. Good? Now, you reach the top and you're stopping up at the top. Okay? You've still got your full weight. But at the top, do you feel lighter or heavier? You're going to feel lighter. Okay? As you stop at the top, you're going to feel a little bit lighter. Okay?
So if the elevator is stopped, you're gonna feel lighter?
No, as it's stopping. Once it stops, you are going to feel the same. But as it is slowing down at the top, you're going to feel a little bit lighter. Okay? Now, you're going to ride the elevator back down. So as it starts going down, you're going to feel heavier or lighter? You're going to feel lighter. So this one's going to be going down as well. Okay? And then when you get to the bottom and it starts stopping, you're going to feel heavier. Okay? So this is stopping at the bottom. Does that kind of make sense? Okay. So, yes,
Where is this elevator? Like,
wherever you want it
It's
to.
only a one-story elevator.
oh really? Or is that?
It doesn't matter.
The faster the elevator goes, the more noticeable this is going to be generally. So if it's an older elevator, they accelerated much faster than our standard elevators now, and so you're going to feel it a little bit
A
more.
lot less smooth.
So,
Older elevators do? They
Yes.
get faster?
old
They feel
elevators in
faster.
like big office buildings are going to be the most accelerating of them because they're not really super worried about the comfort of the person in the elevator. They're worried about getting someone somewhere fast.
No, like the one
That's
in
what I was worried about.
in the Sears Tower. That one goes so fast it hurts your head. Thing zoom.
Where's the Sears?
In Chicago.
It's not called Sears Tower.
The other good one, the one that I've ridden quite a bit, is one of the Drury hotels in San Antonio. I don't know if you've been there. But it's like a 24-story building and it's got really old elevators and they actually accelerate really, really fast.
There's an elevator in one of our hotels that is horrible.
How many people died in elevator like incidents?
I don't know.
Actually, I don't think it's a
All right, so let's start with an example so we can actually get the example in before the bell rings. So we've got a person on the elevator. We've still got the 75 kilograms. Let's say that they're accelerating upward. How much do you want this acceleration to be?
4 meters a second
100
squared.
meters per
No,
second.
4 meters.
No, 100 meters.
We're not doing one on the worksheet.
Dang.
100 meters per second.
100 meters per
How about
second.
5 meters a second squared?
All right, let's do 100 meters per second squared. Okay? I'll close the blind.
Sorry.
I was feeling that when it stops, it's gonna throw the person.
All right. So we're accelerating with 100 meters per second squared upward. Are we going to feel heavier or lighter? We're going to feel heavier. So we want to use the mg plus ma.
Would you die for going that fast?
Yes.
Not die, but you'd probably black out.
the G.
So fighter pilots do sometimes experience, this would be about 10 Gs because it's about 10 times the acceleration of gravity. So this is about the limit where you really, pretty much everyone will black out.
Why?
The
So much
blood
force.
will all rush to the bottom of your feet and stuff, and so you don't have any blood in your brain.
You're on it, you just start to collapse.
Yes.
What if you're laying down?
Then it just goes
Oh.
on you.
You probably wouldn't black out as much.
If you sat down and
I don't
blacked
If
out,
you're going up, like, you use the plus.
What if you're doing a hands-on?
People were distracting me. It should be plus, yes.
Oh,
Yeah.
Okay, so let's say that you're in a fighter plane, right? And you're getting like 10 Gs. In order to stop walking out, would you just like flip the plane over and fly upside down?
then all the blood rushes to your head.
So
Just keep
you
spinning the plane.
just not,
Sit.
You just gyrate the plane.
no, so
Guy, right?
So G's pulling you down and pulling the blood down your body actually handles a lot better than G's going the other way. So it would actually, you just not make as sharp a turn. Because this is a pretty sharp turn very quickly. So,
So like,
all right.
okay,
So here, notice I have rewritten this equation. Okay? So we have W plus MA. Okay? That's because we've already calculated our weight. It's going to be easier this way.
No.
All right, so we get 735.75 plus our mass is 75 times 9.81. And this is going to be our answer. Okay?
8,000.
Now, if it's going down, you're just going to do the same thing. Okay? You're just going to do the minus instead. Okay? That's pretty much how you do the worksheet. The only one that's going to be a little tricky is the last question, part C of the third number on there, because there's really only 3 questions. That one, I want you to think about Newton's third law, and I want you to think about that one for a little while before you answer it. It's not a hard question. You just have to think about it. Good? Tomorrow. Have a good day, guys.
tomorrow?
It is due tomorrow, yes.
Where are you going? Where are you going? That's all.
Miss Green,
Yes.
think it'd be okay if I just stayed for a second physics class?
Well, it's my study hall next, so,
Can I go to the art room? Is that okay?
yes.
Okay, thank you.
Jake, have a good day always. Miss Green, have an amazing day.
You too, Emmett.
See you guys. Adios, Miss Green.